All right, I hope everyone had a pleasant lunch, and now we'll begin our afternoon sessions. 자, 이제 오후 세션을 시작해 보겠습니다. 오후에는 4개의 강연과 1개의 패널 토론이 준비되어 있는데요. 첫 순서로 작년 비들 서울에서도 인사이트 있는 강연을 해주신 카이스트의 김용대 교수님을 모셨습니다. Theoretical and Practical Evaluation of Blockchain 1 Year After 라는 주제로 말씀해 주시겠습니다. 큰 박수 부탁드립니다.
Hello everyone. I gave this talk last year, and then we have more results. So I'm happy to have new presentation on theoretical and experimental evaluation of blockchains. So most of you are either designing, implementing, running, or funding blockchain or business model using blockchain, right? But do you know how good yours compared to others? In my lab with my students, we've been doing actually many different kinds of evaluation technology for blockchain. First of all, we do some theoretical evaluation that shows road to or not to follow. And we do network measurement-based analysis that shows current state of blockchain network. And also, we do traditional security analysis or platform security analysis that shows some of the vulnerabilities. And lastly, we work on emulation and evaluation technology for the future, how we can evaluate different blockchains. So today I'm going to talk about all these four in just 23 minutes left. So why am I interested in technical evaluation of blockchain? First, it is actually very possible we can do technical evaluation because the white paper and academic paper includes theoretical evaluation and all the proofs and sometimes implementations. And many of those blockchains are open sourced. And also, many of the public blockchains, most of you are interested, you can actually join the network and you can actually measure different things. But the reality is actually because you are pretty busy trying to earn money, most of you are not actually putting much attention to the evaluation technology itself. And when I talked to VCs, they said, oh, there's investment war. Right now, we have to actually get the best expert as soon as possible, otherwise we will lose money. So they do have, I will just care about who's the developer, who's the professor, then I'll decide my investment. And also, there's a huge gap between the theory and practice. I mean, many of the blockchain, if you have seen, the white paper and the implementations and the deployed action networks are pretty different. And the gap exists, but actually, we sometimes look at only white paper and without looking at the details about the implementations. And also, lastly, there is the blockchain evaluation technology itself is actually lacking in my perspective. So when I present last year, I had just one paper published, which is one of the theoretical evaluation. And now I have some number of papers published or in submission. I have like 3 more papers published and 3 more papers in submission. And I'll be talking about all these papers except 2, probably 1 or 2. And these papers are actually separated into the red ones are theoretical analysis, green ones are measurement-based analysis, and the blue ones are actually system platform security analysis. And the last one is the evaluation technology we are developing. So let's go one by one. So let's start with theoretical evaluations. We've been writing 4 different papers, but let me talk about only 2 that might be your interest. So this one was published in IEEE Security and Privacy, so-called Oakland. In that paper, we actually look at the fickling among the miners. So between BTC, when the BTC and BCH split, a lot of miners were moving between BTC and BCH. And we were asking, if these people are moving like this, eventually, what would happen to the dynamicity of this miners' behavior? And the paper actually, oops, let's go. We have the main result. We found two equilibrium. There's a one yellow point. Let me start with explaining about the graph. X-axis is a fraction of fickle miners, those people who are moving between the BTC and BCH. Y-axis is a fraction of coin B miners, like BCH miners. And assume one coin B price is equal to K coin A price. So right now, K is about 3%, 0.03. And because fickle miners plus BCH miners plus BTC miners is 1, X plus Y is smaller than or equal to 1. And this is the result. The yellow dot is actually one of the equilibrium where BTC miners and BCH miners are stably coexist. And on the bottom, you see there's a line between dot K0 to 1, 0. This is the line of equilibrium, where once we reach that line, then there exists 0 BCH miners. So there could be two equilibrium. One is that point that shows the stable coexistence of the BTC and BCH. And the bottom line, when we reach the bottom line, basically you're going to have 0 BCH miners. So this, and the arrows showing that once you are in zone 1 or zone 2, you will be moving to stable coexistence. But if you go down to zone 3, it will make BCH collapse in terms of the miners. So you can look at the paper in detail, but actually we also do the measurement of the time right after the BTC-BCH split. And at that time, there were huge actually fickling among BTC miners and BCH miner. And we plotted the points on the graph. And it was actually, when you look at the zone B, zone C, zone D, zone E, and F, actually it was going to the direction of the BCH collapse. And luckily, BCH decided to do new difficulty, deploy new difficulty adjustment algorithm. And there was in graph H, there was a hard fork in BCH that moved the point to the good zone. And right now, BCH and BTC are stably coexist in terms of the mining, even though the price is decreasing. But in the paper, we did actually prove another thing, that when K% of miners are involved in automatic mining, then BCH will be endangered. The day before yesterday, K was about 3%. So what is automatic mining? I think some of the people working in the mining industry, they are trying to help miners to get their best profit. And one way to do it is based on price and the difficulty, you automatically choose which coin to mine. We basically proved that if 3% of miners are moving automatically, then BCH will die. What about ETC versus ETH? So even in case of ETH, so our analysis actually depends on what kind of difficulty adjustment algorithm. The same analysis works if ETH change its difficulty adjustment algorithm to BTC, then other Ethereum variants will also suffer from the same problem. For the detail, you can take a look at the paper. And the next thing, we've been recently working on incentivization versus decentralization debates. A lot of people know that once we start incentivizing, I mean, when Satoshi come up with POW, he introduced incentivization to increase the decentralization. But it turns out that actually, Bitcoin is being centralized. So introduced incentivization to increase decentralization, but that are leading to centralization, right? And our question is this really generic? That if once you start doing incentivization in any permissionless blockchain, will it be centralized? Some people have the insight, and for example, Silvio Micali has the insight that, yeah, we are not doing incentivization because it will lead to centralization. But is there any security proof or theoretical proof? And we come up with the two most important requirements for the full decentralization. Some of the people agree on this, or some of the people don't agree on this. And these two requirements can be expanded to 4 different requirements. And this is a sufficient condition. So the first condition is node with any resource power can earn net profit. And the second is delegation should not be more profitable. Third is civil should not be more profitable. And the resource power ratio between the any two nodes conversions, the resource power should be converged to 1 or very close to 1. So we want pretty flat power to make it full decentralization. And we actually proved that once any blockchain satisfies these 4 conditions, then it can reach the full decentralization. But unfortunately, we also proved that satisfying all these 4 conditions at the same time is impossible. So if you're interested, take a look at the paper. Whew. Now, this is a network measurement-based analysis. So, somehow we got interested in Stellar. And this one was presented in a workshop in IEEE. And we were interested in Stellar's liveness. So we were interested in Stellar, so we basically put some nodes in Stellar and basically collect the data, network architecture of the Stellar. And as you heard, the Stellar is actually quite centralized, and these red nodes are run by the Stellar Foundation. And when we measured, actually, Stellar was actually quite centralized. And what we found is that there is some kind of domino effect, or we call it cascade failure, that 2 of this Stellar Foundation node dies, then the whole Stellar network will collapse, or they cannot produce any block. So that was the result in the paper. And so after our paper got accepted, we actually contacted the Stellar Foundation. And David Measures has responded to us, and they say, oh, we value safety more than liveness. And there were a lot of discussions in the Reddit. And so actually, even if he said that, but actually the Stellar network start doing decentralization. So they put a lot of manual effort. As you know, the Stellar requires manual effort to decentralize it. So they put a lot of effort to decentralize it. So, and around May 1st, actually, 2-node failure does not actually increase to any collapse. But there were 251 cases of 3-node failure lead to 100% cascade failure. I don't know, like 3 cases of 2-node failure versus 251 cases of 3-node failure. I don't know which one is better. But anyway, they were improving in terms of 2 versus 3. But on May 15th, actually Stellar died. Because of the exact same reason we focused it, the cascade failure. And actually, this is the Stellar died for 2 hours, and it could not produce any block. And so on the same day, about 20 hours before actually Stellar collapsed, we actually collected the data about the network. There were 28 cases of 2-node failure were leading to 100% failure. And one of those 28 cases actually happened. That's why the cascade failure happened inside the Stellar and died. This was what happened. And we do some system security analysis. This is actually the first time I talk about it. because the paper just got accepted to Usenix security, Usenix UT, the workshop on offensive technology. And this is, in here, we analyzed the EOS resource management. The paper will be available around May, and so please take a look at it when the paper is published. We come up with actually 4 different attacks. One is called block delay attack, and the second and third is a CPU and RAM drain attacks, and the fourth one is ransomware attack, where the attacker can drain customers' RAM very quickly. So this will be actually published in Usenix UT, and I think the paper is actually pretty interesting. And the first attack, I'll be talking about just the result, not the details. So the first attack, the attacker put 2,368 EOS as a stake. Then using that stake, you can stop the EOS for 9 minutes. Stop the EOS for 9 minutes. That is accounting for 181,000 EOS. And we found this vulnerability, and of course we reported to EOS. And they give me some good bug bounty, $15,000. Not 181,000, but I mean. Anyway, so this is one of the attack, and this is actually very interesting. I mean, this happened because the EOS tried to process the smart contract as soon as possible. And this is another attack called RAM drain attack. Within 30 seconds, we can actually drain the RAM, 20 megabyte of RAM of a smart contract actually very quickly using this attack. And the last one is a ransomware attack. And within 22 seconds, we can actually drain users 2 gigabytes of memory within 22 seconds. And this is the maximum memory a user has inside EOS. So if you're interested, take a look at the paper once it is published. It is not available right now because we are still communicating with the EOS right now. And the last piece, I have 7 minutes, 50 seconds. So last year we talked about BLEEP, Blockchain Emulation and Evaluation Platform. And so I think, as I've been saying, the blockchain needs evaluation. Because well-organized evaluation can reduce the unpredictability. But the blockchain evaluation is actually quite difficult because the blockchain network is actually very large and also very decentralized. And also P2P is actually unpredictable. And we don't know exactly what's going to happen in each of the blockchain. So we want to develop some kind of evaluation technology which is cost-effective and scalable for evaluating large-scale network. And we want to have reproducible evaluation technology for unpredictable peer-to-peer network. Like, something happened and you start debugging and you have no data how you debug, right? So that's why we want some kind of reproducible evaluation. And also we want some kind of standardized evaluation platform where you can actually compare different blockchains. This may not be the actually good platform to evaluate very high-scale smart contract platform. For the consensus algorithm perspective, I think this could be a pretty good candidate. So I'm thinking about 3 customers. The first customer is the student. When I think about the students, I don't know, many of you are the student who are working in the blockchain, who used to be a student, who are now working in the blockchain company. But did you ever implement like 1,000 node Bitcoin, experiment 1,000 node Bitcoin as a student? Probably not, because the Amazon cost is too expensive, and probably you have no platform to test 1,000 node Bitcoin network, right? And so when you start working in the company, then basically you have no experience of actually implementing the blockchain. So I want to provide some kind of platform for students who can actually experiment distributed system. And we want to provide some kind of skeleton blockchain so that students can implement their own blockchains or as part of the class. Oops, I'm sorry. Yeah, as part of the class. Or students can do research with this platform. So in some sense, if you're a computer science student who has experience in operating system, I want to provide some kind of nachos or pintos kind of skeleton operating system. Instead of skeleton operating system, I want to provide skeleton blockchain and networking platform where students can implement them. Even for developers, I've been talking to actually many of the developers and many companies. Actually, they said debugging and testing is actually a huge headache. And because many of the blockchain have to be fault tolerance, but implementing the middleware to inject fault is a pain in the ass, and everybody has to put some kind of they have to put, huge effort to implement the, failure injecting module, right? And of course, even if you're working on testnet, you're gonna spend tons of money at Amazon, right? Before it is actually being stabilized. So I want some kind of platform where developers can test large-scale network on a single platform. And also, in the long run, I want to provide some kind of platform for VC and DEX. Maybe for a testnet case, they can check whether each of the blockchain who want the funding from them can test how good they are. So let's get. So our blockchain platform has actually multiple modules. The first is a meta blockchain, and this meta blockchain has multiple things. It has the neighborhood discovery, different gossip modules, different consensus algorithms, and traffic generators, transaction generators, and we also have network emulator that supports network emulation. So the emulator we use is called Shadow. Shadow was actually implemented by one of my former students who developed Shadow for actually Tor experiments. But I realized that actually the Shadow can be used for blockchain emulation, so we are now modifying Shadow. And actually, in the long run, right now, Shadow is only supporting C++ blockchain. So unfortunately, not many of the blockchain can be supported. But in the long run, we want to develop language-independent emulation where you can run different blockchains without modification. And we want to provide dynamic network topology change or dynamic fault injection so that actually you can do standardized failure testing and performance testing on it. And of course, we want to have an evaluation layer so that we can provide different transactions and different topology to test. And some visualization to support centralized debugging and those kind of things in the single platform. So right now, the work is going pretty well. Right now, we have a few experiments. We run 6 nodes in EC2, in different continents, and that requires about 7.5 cents, okay? And for 1,000 nodes, probably you will be spending $120 on Amazon. But on our emulation platform, it's a single host, so it costs about 30 cents. So this is actually very, very cheap. And the fork rate and different things actually show that we are actually very close to real life. And also, my students I use this in my class, and some students actually tested different gossip algorithms, such as random and plum tree gossip algorithm. And they come up with this table showing the trade-off between the random gossip versus plum tree gossip. And also, we also did, this is actually, Eclipse attack. So we launch Eclipse attacks, and usually once you experiment network attacks on blockchain, then probably there is no platform to do it. But on our platform, we could actually test the Eclipse attack as well. And to improve the performance, the current bottleneck for our platform is actually memory, and we are actually providing deduplication, and we are actually implementing more and more deduplication to provide higher scalability. Right now, we are scaling up to about 2,000 node Bitcoin network. So conclusion. So yeah, I'm interested in blockchain technology evaluation technology in terms of theoretical evaluation, network measurement, and platform security analysis, and lastly, emulation evaluation technology, so that we know how good your blockchain is. So ask us about your blockchain, and we will do it for you if you give me some money. Thank you very much.